Hi, everyone. So today we have Jonah Blasiak from Drexel University, who will be talking to us on a raising operator formula for nabla on an LLT polynomial.
All right, so thank you to the organizers for inviting me to speak here. Just everyone, please feel free to interrupt me with questions. I can only see like 4 people right now, so it's hard for me to get a good gauge of the audience. And also, I'm not good at monitoring the chat, so if anyone sees a question in chat that they want to let me know, just feel free to interrupt.
I'll moderate the chat, so if anyone asks, I'll read it out for you. Don't worry.
Okay, thank you. Okay, so, all right. So the main result that I want to tell you about today is a construction of certain symmetric rational functions, h nu, depending on a tuple of skew shapes nu. And these symmetric rational functions live in an algebra called the shuffle algebra. And they have the property that when you take their polynomial part, you get omega nabla applied to the corresponding LLT polynomial. Okay, so I want to start the talk by telling you about certain functions we called Catalan functions, which are symmetric functions with a single parameter q. For context, these h nu we construct have a parameter q and t. But the Catalan functions are functions that my collaborators and I have been studying for several years now. And they're maybe not strictly necessary to understand the theory I'll tell you about today, but I think they provide a useful context and sort of warm up for this main result. Okay, and then after that, I'm going to tell you a little bit about sort of a broader context for this result involving the elliptic Hall algebra and shuffle algebras. And then we'll go on to see sort of specifically how do we get this kind of result, and it involves combinatorializing some results of Nagu on the shuffle algebra. And then I'll talk a little bit about applications. Okay. Okay, so I'm just trying to look at some of your faces. Most people have their cameras off. Okay. All right. So Catalan functions. These are a family of symmetric functions. As I said, they're defined over a single parameter q. Originally studied by Panyushev and Mark Heyman and his student Li Chung Chen. My collaborators and I have been studying these for several years now. So it's quite a general class of symmetric functions. They contain the modified Hall-Littlewood polynomials. These are the symmetric functions whose Schur expansions are the Q-Koska coefficients, as well as certain parabolic generalizations of these symmetric functions. They're equal to graded Euler characteristics of certain vector bundles on the flag variety. And the definition that I'll give is purely algebraic, but it's essentially the same as this description. One of our main results concerning these functions was showing that they contain as a special case the K-Schur functions. And we were able to use that to give a combinatorial formula for the expansion coefficient, the Schur expansion coefficients of K-Schur functions. Okay, so now a natural question or idea is to try to develop a QT generalization of these Catalan functions. And I think in some previous talks I've given, some people have asked about this. And we started working on this about 2 years ago. And in some sense, this talk is an answer to that question. And you kind of can do it, but the theory is not quite parallel, at least not yet. So it kind of took on a life of its own, and we don't really have a common generalization of the results that we know for Catalan functions and the stuff that I'm going to tell you about today. Okay, but I think it still serves as a good warm-up. All right, so we're going to be working in, oh, sorry, I should put on, can you see my mouse?
Yes.
Yes. All right, I'll just use that, all right, instead of the Zoom pointer. All right, okay, so we're going to be working in the ring of Laurent polynomials in L variables, or sometimes this larger power series ring. So we have a symmetric group in L letters, acts by permuting these variables. We're going to let R plus denote the set of positive roots for GLL. So alpha ij is the vector of length L with a 1 in position I and a -1 in position J. The Weil symmetrization operator is given by either of the following two formulas, whichever you prefer. This second one is maybe the more familiar version. If you plug in f of z to be a dominant monomial, then you get out, like say z to the lambda, you get out the corresponding Schur function s sub lambda. This version here is just a slight rearrangement, and it's maybe a little bit better for what we're going to talk about. Okay. So first thing to understand is what happens when you take the Weil symmetrization operator and apply it to a monomial. Okay, so this we'll call this Schur function straightening. So if you apply sigma to some z to the gamma, you get either a Schur function up to a sign or 0. And here are two examples. So if gamma is 3, 1, 2, 5, the recipe is what you first do is you add the vector rho, L minus 1 down to L minus 2 down to 0. And so in this case, you get 6, 3, 3, 5. And then you take this vector gamma plus rho, you ask, does it have a repeated part? If it does, then the resulting Schur function straightening is 0. Okay, and so here's an example where that doesn't happen. Say gamma is 4, 7, 1, 6. What you do is you add rho, then you sort it to be weakly decreasing, and then subtract rho, and that's the resulting Schur function you get. And then the sign comes from how many transpositions did you need to sort this, this gamma plus rho. Okay. All right, so the definition of the Catalan function is as follows. So we take some subset of the positive roots psi and a weight lambda in z to the L. And then we take this rational function with the denominator 1 minus q z to the alpha, product taken over all the roots in our chosen set psi. And then we apply this symmetrization operator and then take the, then we view this as a series, okay, and take the polynomial truncation, which means that we throw out any Schur functions that are not indexed by non-negative integer weights. Okay. So as a sort of the two extreme examples, just to get some idea of what these are, if you take the empty set of roots, well, then this is just the Schur function straightening again. And if you start with a partition weight, then you just get the Schur function lambda. If you take the full set of roots, R plus, then you get the modified Hall-Littlewood polynomial. This is a known, but maybe perhaps not so well-known description of the modified Hall-Littlewood polynomials. Okay. So with the full root set, you kind of tend to get the biggest Schur expansions, and then smaller root sets, you get smaller Schur expansions typically. Okay, so here's a specific example. And we like to draw these Catalan functions with the weight down the diagonal like this. So for this lambda is 3, 3, 2, 1. And then we mark the set of roots. In this case, we've chosen 3 roots. We mark these sort of in their matrix positions in this diagram. Okay, and this is our picture of what a Catalan function looks like. And then, by the way, so it's kind of funny. So to simplify the discussion here, I just chose this to be an arbitrary subset of positive roots. Normally, in previous work, we've defined this to be an upper order ideal of positive roots, which means it has to be sort of upper right justified in this picture. And that's where the name Catalan function comes from, because there are Catalan many such upper order ideals. But for this talk, it couldn't really be any subset. It doesn't matter. Okay, so all right, so let's just see what we get when we try to evaluate this Catalan function here. So here's expanded out the definition, and now we want to take each of these, 1 minus qzi over zj inverse, expand this as a geometric series, like 1 plus qz1 over z3 plus q squared z1 squared over z3 squared, and so on. And then we truncate to only polynomial characters. So it's not hard to see that sort of once you start applying, Zi over Zj to some large power, you get things whose polynomial truncation will be 0. And sort of these are the terms that are maybe obviously not 0. Some of them do end up being 0. So now we look at this series. So take, for example, this 3, 4, 2, 0. Let's just see, where did that come from? Well, that came from starting with the vector 3, 3, 2, 1, and then multiplying it by Q Z2 over Z4. Okay, that's how we got the 3, 4, 2, 0. Anyway, so we get all these terms like that. And then we do the Schur function straightening and take the polynomial part. So for example, this 3, 4, 2, 0, this ends up going to 0 when we straighten, like this 6, 3 minus 1, 1 ends up canceling with the Schur function straightening of 6, 3, 0, 0, and so on. Okay, and at the end we get this, turns out to be Schur positive symmetric function. Okay. So part of why I'm telling you this is just to see why these kinds of rational function type expressions can be quite useful for generating like large classes of symmetric functions. Okay. All right, so now that we have this sort of one parameter case in mind, let's move to two sets of variables. So now we call these objects kettle animals. Okay, so now there are three pieces of data, or three root sets, RQ, RT, and RQT, together with a weight as before. And again, we have the 1 minus QZ alpha in the denominator. We have an additional factor 1 minus TZ alpha in the denominator. In the numerator, we have these 1 minus QTZ alpha factors. Okay. For these guys, we're not taking the polynomial truncation. It just turns out to be sort of cleaner if we develop the theory without that, viewing these as actually symmetric rational functions. And then later, for some applications, we'll need to take the polynomial part. Okay, so let's just give a few small examples of this. So when L is 2, here's one example. And then we can just expand this as a series if we like. So expand these denominator factors as series and then take the Schur function straightening, and what we get is this. This is without the polynomial truncation. Okay, and if you want to take the polynomial part, it's just these first two terms here. Okay, here's a bigger example. So if we take the Q ideal and the T ideal to be all of the positive roots, L is 3, and the QT ideal to be just this single root 1, 3, this is the kettle animal written out. And we can evaluate it just like before. Well, it's going to be an infinite series, but let's see what happens when we take the polynomial part. Okay, so we get, it turns out, this symmetric function. And some of you may recognize this. Well, do any of you recognize this? Yes. I can only see a couple of you. But
is that a modified McDonald polynomial, maybe?
Not quite, but that's, you're in the right ballpark. So it's actually omega nabla E3.
So I have a question with the RQ, the RT, and the RQT.
Mm-hmm.
They can be any subsets. Do they have any relationship between each other?
They can be any subsets. They have no relationship between each other. Typically, they will be upper order ideals, like in this example. Sort of all of our interesting examples of kettle animals, they're upper order ideals, like upper right justified subsets of the roots. But as for the definition, we allow them to be any subsets.
But the QT symmetry in this particular case comes from the fact that you picked Q and the RQ and RT to be equal?
That's right, exactly, yes. That's a good point. So if RQ and RT are equal, this is automatically QT symmetric. Now it can happen in interesting ways that you get something QT symmetric out when the input is not obviously QT symmetric. Okay, other questions? Okay, so now I want to give a sort of overview of LLT polynomials in order to define a special kettle animal related to LLT polynomials. Okay, so these are defined for any tuple of skew shapes, nu1 up to nu k. We denote it by this g cal nu. They're symmetric functions in a single parameter q. When we specialize q to 1, we just get the product of the Schur functions corresponding to these skew shapes. These were first defined by Lescaut, Leclerc, and Thibon in terms of ribbon tableau and related to the representation theory of UQ SLK hat. Later on, they were shown to be Schur positive when the nui are straight shapes. The coefficients in the Schur expansion were shown to be essentially Kazan-Lustig polynomials by Leclerc and Thibon, and later by Gronowski and Heyman did the general case also using Kazan-Lustig theory. Okay, so that's just a brief overview. I want to actually get now into the specifics of the definition because they're going to be important for the construction that follows. And this is the sort of attacking inversion description of LLT polynomials, not the original ribbon description. Okay, so first of all, let's take our tuple of skew shapes. Okay, this is our example. And these grayed out squares are the ones that are not in our skew shape. They're in sort of the lambda / mu. This part is the mu. And so here there's two elements in this tuple. And it's convenient to align their contents in a single picture to just put them on the same XY plane as we've done over here. Okay, here are the contents. That's column minus row in each square. All right, and then we're going to give these an ordering by reading by diagonals. So we read sort of starting in the top left, we read by diagonals up and to the right like this, B2, B3, B4, B5, B6, and so on. So these are labels for the boxes, okay, in this reading order. We say that an ordered pair AB is attacking if A comes before B in reading order and one of two things happens. Either they have the same content as in this example. So here B2 and B3 have the same content. So B2 attacks B3. The other thing that can happen is they can have contents differing by 1. Here B3 attacks B4. The extra condition is that basically the first guy in the attacking pair has to occur in a later element of the tuple. So for instance, B3, B5, even though their contents differ by 1, is not an attacking pair. Okay, so here are the remaining attacking pairs. B4 attacks B5, attacks B6, and so on. Okay, and now we can define the LLT polynomial. So this is just like in the combinatorial definition of a Schur function. We sum over all semi-standard fillings of this, in this case, this pair of shapes. So that's weakly increasing in rows, strictly increasing in columns. But together with this extra statistic, q to the inv. Okay, and inv here counts the number of attacking inversions in each tableau. So here's an example. Okay, so let's just go through each attacking pair and check whether or not it's an inversion. So the definition is that if the attacking guy you start with is if the filling in that is less than the one you end with, then that's not an inversion. If it's greater than it is an inversion. Okay, so here 5 is greater than 3, that's an inversion. 3 is greater than 1, inversion, and so on. Okay, so of the 7 attacking pairs, 4 of them are inversions. So we get this inv of t as 4, and this contributes a q to the 4th power here times this monomial in the sum. All right, so now that we have that definition down, we're going to use this to define a very specific, sort of very interesting cattle animal. Okay, so all of our cattle animals that we consider in this talk will satisfy this additional condition that RQ contains RT contains RQT. And because of this, it's going to kind of be convenient to then, instead of thinking of what are these root sets, it's equivalent to sort of say, what are these set differences, okay? So now the way we describe this cattle animal is as follows. So the set difference are the full root set minus the Q root set. In other words, the non-Q roots. These are sort of correspond to pairs of boxes in the same diagonal. Let me actually flip to an example now. It's more useful. Okay, so here I have my tuple is just a single shape. So this is the case of a Schur function LLT polynomial. Okay, and here's the diagonal reading order, like we talked about before. All right, and now these black squares indicate the Q non-roots, and this is sort of like parabolic blocks whose sizes correspond to the diagonal lengths of this shape. Okay, 1, 2, 3, 2, 1, 1. And that's what these black squares sort of cut out here. Okay, the next thing we need to pay attention to, there are no attacking pairs in this example, so ignore that. In other words, RQ equals RT in this example. Then these gray dots indicate these stand for the T ideal less the QT ideal, and these are the glue between adjacent diagonals. Okay, so for example, these 6 gray dots here, these correspond to the 6 pairs of B2 and B3 go to any of the 3 boxes on this next diagonal. Okay. All right, and then finally, I need to tell you about how to get the weight here. So the weight lambda that's written down the diagonal here is as follows. So it's actually better, it's sort of more convenient to think of the weight as a filling of this shape, okay? And then to get the weight, the actual weight, we read it by reading order. Okay, so this on the diagonal is just the, this weight read by, this filling read by reading order. All right, so what is this filling? Well, on each diagonal, it's constant on diagonals, first of all. And then on each diagonal, we take 1 plus 1 if there's, if the diagonal contains the first box in a row, and minus 1 if the diagonal contains the last box in a row. So this main diagonal here contains the first box in a row and the last box in a row. So those cancel out, and we just get this, this original 1 here. On the other hand, this next diagonal here does not contain the first box in a row, but it does contain the last box in a row. So we get 1, 0, minus 1. So we get a total of 0 on this diagonal. So that's the recipe for the weight. Okay, so this, I'm going over this slowly because this is really in some ways our main result. Like finding this object was really the biggest thing. It's kind of amazing that such a thing kind of exists. Well, once I tell you the main result about it. But let's go on to another example. Okay, so here is one for the skew shape, the tuple of skew shapes we had before. And so now, well, just as before, the diagonals of each individual shape come out to be these blocks in the parabolic shape, which is R plus delete RQ. So here there's only one diagonal of length 2, that's indicated over here. And then same as before, the gray dots are sort of the glue between adjacent diagonals. So this 2, 0, 2, 0 that's connected by these gray dots, this is this ribbon shape over here. Okay, let me go to the next slide. And then these red squares are the attacking pairs. That's RQ delete RT. So for example, this box, which is the second box in reading order, whoops, attacks this box B3. So B2 attacks B3. That's indicated by this red square over here. Okay. So we have sort of all of the data of an LLT polynomial is encoded in this rational function in a weird kind of way. And somewhat miraculously, it's almost like we can develop the combinatorics of the LLT polynomials sort of independently. Like it's possible that in some alternative universe, these cattle animals would have been discovered first and then actually led us to finding the LLT polynomials because somehow this construction ended up being very natural.
Okay. I have a question, is that okay? On the previous slide, so what is the actual data on the right-hand side you need to, in this diagram? I mean, there's a dict path somewhere in there that describes the gray cells, but I guess the labeling on the main diagonal is like the extra data that you need also?
Yeah, so like you have to trace back, to this definition. So the weight in the original definition, this weight lambda, that's the one on the diagonal here. And then these three root ideals specify these denominator and numerator factors. And that's sort of all encoded in that picture. But
okay, and every LLT polynomial nu can be represented in this way?
yes.
Yeah, okay.
That's great.
But is there a way to, I mean, so the nu is sort of encoded in this diagonal also in some sense, I suppose.
In the diagonal, what do you mean?
Yeah, the labeling did like 2, 0, 2, 2, 1, 1, 0, 0. That's
right. I mean, some additional information is encoded in this. Yes, yeah, so you can't actually determine from the root sets alone. You can't determine the LLT polynomial. So actually, every ribbon shape, if you just take a single ribbon shape, those all have the same root sets, but the weight actually specifies. Right, it's because of the way this comes out, it kind of specifies how the ribbon, whether it goes horizontal or vertical steps.
Yeah, I see.
Yeah.
I have a question too about the row start and the row end. So now that you have multiple diagrams in there, you can contain multiple row starts on a diagonal, but you still only contribute one to that.
I see, sorry. Yeah, good clarification. So when I was talking about diagonals, diagonal here means a diagonal of a single shape. So the definition is really the same as before. You take each shape separately and you do the same computation we did earlier. So these don't count as the same diagonal. Like the shapes don't interact for this computation.
And then I think Andrew had a question as well, but I should also warn it's the 25-minute mark, Jonah.
Okay, this is a good time, I think, to take a break.
Is a good time?
Yep.
Okay. So after Andrew's question, we'll take a 5-minute break. So Andrew is asking, do these diagrams, the one on the right, characterize tuples of skew shapes? Or?
That's a good question. Yeah, so we haven't really thought about it like that. It's possible. My guess is that the answer is yes, but we would need to sort of describe intrinsically, like what properties do you need to have to be an LLT kettle animal, right? And then you could say, okay, if you satisfy these properties, then you can recover the tuple of skew shapes. We haven't actually done this, but my guess is that you could.
Thanks, Jonah.
All right, so here is our main result. Well, it's actually really a correlator to other stuff, but it's sort of our easily said result is that if you take any tuple of skew shapes nu, then omega nabla of the associated LLT polynomial is equal to the polynomial part of this LLT kettle animal that we just defined. Okay, up to some constant, some power of q and t with a sign, which we can specify, but I'm not going to tell you here. Okay, so now I want to give you some sort of broader context for this result and maybe hint a little bit at how we prove this, or at least how to understand it better. Okay, so for any, or for an abelian category A, it has to satisfy suitable finiteness conditions. Its Hall algebra has underlying space, vector space with basis given by the isomorphism classes of objects in A. And the product is basically encodes the number of extensions. So the product of isomorphism class of A with isomorphism class of B encodes the number of extensions of A by B. Okay, so here's the formula. This extra factor here is called the Euler form. And so this is a very general construction for any abelian category, or not any, but many abelian categories. And sort of its original, it was originally studied in the context of the category of finite abelian P groups. And in that case, the Hall algebra is isomorphic to the ring of symmetric functions. And this distinguished basis that comes from these isomorphism classes is actually essentially the Hall-Littlewood P polynomials. Okay, so this construction, was sort of originated in the work of Steinitz in the 1900s and later, much later in around 1950 by Philip Hall, working independently. They defined it first in that special case where it's isomorphic to the ring of symmetric functions. Okay, so hence the name Hall-Littlewood polynomials. But you can actually get some very interesting things by taking fancier abelian categories here. So, and this idea, I think, was initiated by Ringel, who related it to quantized enveloping algebras. But Bourbon and Schiffman studied the Hall algebra of elliptic curves, the Hall algebra of coherent sheaves on an elliptic curve over a finite field. And actually they went further by looking at a certain subalgebra of this Hall algebra. Somehow, I don't know exactly why this was sort of the right thing to do, taking this subalgebra, but somehow that seems to give a very nice theory. They were able to give explicit description of this. So this algebra E, we'll call this the elliptic Hall algebra in terms of generators and relations. They also described sort of a PBW type basis for it. And now for us, we're not going to go into many details on this, but one sort of takeaway thing from this construction is that this elliptic Hall algebra is generated by certain subalgebras, lambda of xmn, each isomorphic to the ring of symmetric functions, where m and n are any coprime pair of integers. Okay. All right, so we want to get a sort of more concrete and combinatorial understanding of this elliptic Hall algebra. And so the one good way to do that is to study another algebra called the shuffle algebra. Okay, so this is a sort of summary here that I'm going to explain to you in the next few slides. Okay, so this direct sum of symmetrized Laurent polynomials in increasing number of variables, we call this the big shuffle algebra, which with a certain product that I'll soon define. Okay, and maybe I'll start by telling you about this map. Okay, this bottom map here. So this is a sort of gamma symmetrization map, and it's defined component by component. So on the Lth component, sigma gamma to the L is sort of looks like the normal symmetrization over all elements of the symmetric group, but you add in these additional factors, gamma zi zj, where gamma is this sort of carefully chosen function, rational function in two variables. Okay, so this thing you end up with is some symmetric rational function, and it has these with these sort of strange extra factors added on. Okay, so now not only is this gamma symmetrization a linear map, but you can also make it into an algebra homomorphism for the following products defined on both sides. So on the left, we define we take this direct sum of rational function spaces to have the product not given by sort of normal multiplication in these rings, but actually by the concatenation product defined as follows. And then on the other side, we take what's called the shuffle product on these symmetrized Laurent polynomials. So there should be a direct sum here. Okay, so we start with the concatenation product, and then we multiply by this sort of rectangle's worth of these extra gamma factors, and then we symmetrize over all shuffle permutations because, well, we only need to symmetrize by that much because these are already symmetric in C1 in 1 up to k and in k plus 1 up to L. Okay. All right, so this shuffle product, one way to think of it is kind of what you need in order to make this linear map an algebra homomorphism. All right, and then we define the shuffle algebra S to be the image of Laurent polynomials under this gamma symmetrization map. Okay. So now we could have just maybe skipped ahead to this definition, but it's nice to think about this big shuffle algebra too. So this is also a useful thing to consider. Even though we're sort of really after the shuffle algebra, it's easier to describe sort of the total space here. Describing this total space of the shuffle algebra explicitly is actually harder. And we'll see an example of kind of the subtlety there. To connect this back to Catalanimals, notice that if you gamma symmetrize a monomial z to the lambda, you get the following. So this comes from, if you notice this form of this extra factor gamma, it has sort of all the pieces of a Catalanimal in it. And this 1 minus zj over zi, this actually contributes to the Weil symmetrization operator. So this is the same as the definition we gave before, but this 1 minus z to the minus alpha and the symmetrization, those together are the Weil symmetrization operator. So this turns out to be the Catalanimal corresponding to when all of the root sets are the full R plus. Okay. And this does indeed live in the shuffle algebra basically by definition because it's the gamma symmetrization of a monomial. Okay. Now, here's something else, something closely related, but just to give an idea of sort of what can happen here. So this symmetrization can lie in the shuffle algebra even when f is not a Laurent polynomial. So, right, this map, this gamma symmetrization has a kernel. So if there's something in this space that differs from something in the Laurent polynomials by something in the kernel, then, well, it still lands in the shuffle algebra. And that actually happens in sort of interesting examples that are relevant for us. So Nagu showed that for this example, when you gamma symmetrize z lambda divided by this denominator factor, we just go back a slide, what that amounts to is when I put in this extra denominator factor, it cancels out some of these qt roots in the numerator here. Right, this is just a linear operator, so it carries through and then cancels out some of these roots. And what you get in the end is the Catalanimal where now the qt root ideal, this is basically almost all of the roots except you've deleted like a diagonal's worth of them. Okay. And just sort of not related to this comment, but just notice that this Catalanimal is one we considered before. Actually, the special case we considered for L equals 3 in an earlier slide. Okay. Okay, but basically one of the sort of points here is this thing here where gamma symmetrizing is not Laurent polynomial, but yet this still happens to lie in the shuffle algebra, but not in an obvious way. It's actually, this is hard to show, and it's not easy to see like what Laurent polynomial is this equivalent to modulo the kernel of this symmetrization operator. Okay, so to further connect sort of the shuffle algebra to the Catalanimals, here's an interesting observation. So notice that any Catalanimal of length L lies in this space of symmetric rational functions, okay, because we define them by symmetrizing. They don't all lie in the shuffle algebra though, so that they lie in the big shuffle algebra, not the shuffle algebra in general. But we have a nice interpretation for the product in the shuffle algebra, or rather, sorry, the product in the big shuffle algebra. So here's, let's take two such Catalanimals. These are the Catalanimals for these shapes, the LLT Catalanimals. In this case, I'm just using a single tuple, so there's only one element in the tuple. And basically, the shuffle algebra product is just you take the two Catalanimals and you put them catty corner like this. And then everything in here, this is sort of all the possible roots, sort of the root sets RQ, RT, and RQT we take for this entire rectangle. So that corresponds to this. these gamma factors in the shuffle product, okay? So now we can think of in terms of pictures, sort of what the shuffle product looks like, at least on cattle animals. So, by the way, maybe to just put some broad context here, what we're trying to do is we're trying to sort of make the shuffle algebra more combinatorially explicit by introducing these sort of very rich combinatorial objects, right, defined by these three separate sets of roots, okay? Okay, and we're going to take that, we're going to continue with this idea in the next few slides. Okay, so an important result is proved by Shifman and Vasserode is the following. The shuffle algebra is isomorphic to a certain subalgebra of the elliptic Hall algebra. It's the one generated by sort of the right half plane alphabets. Okay. Okay, so now our goal is to kind of make this get a more concrete understanding of the elliptic Hall algebra, and the shuffle algebra is a good way to do this. But now if we want to sort of move over and work entirely inside the shuffle algebra, then one way to think about it is, okay, well, all right, how much can we kind of forget about the elliptic Hall algebra? It still offers a lot of useful information coming from the geometry, but kind of the main thing that we want to take from that, at least for the purposes of this talk, is the following. So it means that this shuffle algebra S comes with sort of distinguished subalgebras. So these lambda x mn's, these for each coprime pair of mn with m greater than 0, we have one of these distinguished subalgebras. And then, so there must be a corresponding one on the shuffle algebra side. But kind of the interesting thing here is these are not easy to describe directly on the shuffle algebra. And that's kind of what we're going to turn to. So Nagu did a lot of work on this, and we take Nagu's work a bit further. All right, so we're going sort of all out with the animal theme here. We say that a cattle animal of length L is cuddly if it satisfies the following three conditions. Okay, so this is one of our key definitions for sort of combinatorializing the shuffle algebra. So let me just explain some of this notation. So if we have a subset of roots, A, we let A to the JK denote the roots that go from the set J to the set K. That's what this notation is down here. And then let me just say a few words about this first condition. So I like to think of this in terms of just directed graphs. So instead of thinking of this as a subset of roots, we can just think of it as a subset of directed edges. So there's sort of Q edges and T edges. And what this means is that if we follow a Q edge, or if we start with a Q edge and follow it by a T edge, then we have to land in a QT edge. And similarly, if we start with a T edge and follow with a Q edge, we have to land in one of the QT edges. So that's the first requirement, okay? Second requirement is that the total weight has size L. If you notice, our LLT cattle animals sort of automatically satisfy this the way they were defined. Okay, and then this last condition, I'm going to give an example of in the next slide. Okay, so in our simplifying assumption that is common, we're going to assume RQ contains RT contains RQT. Then this formula that I had on the previous slide simplifies. And here's just an example of what this looks like. So here's the LLT cattle animal for just a single Schur function S22. Okay, there's no attacking pairs here. If I take the subset J to be the set 1, 2, then here's how we compute this sort of augmented weight lambda bracket J. So first of all, we take all of the roots and we look at the ones that go from the set J to the complement of J. That's just given by this sort of squares worth of roots here. And then in pictures, lambda bracket J is the following. So we take the weight lambda, we add in the sort of Q non-roots, that's this contribution here. We want to think of this as adding the vector corresponding to this root, and then we subtract the ones corresponding to the T delete QT roots, okay? Those are these two gray dots. And when you add it all up, you get this weight 1, 1, 1, 1. All right, so here's a few more examples for all the subsets of a size 2. Here's this sort of adjusted weight lambda bracket j. And then what do we need to check for this cuddly condition to hold? We have to look at the subset of this vector corresponding to j, and then add up those entries. Okay, so this is what we've done here. So these numbers down here are just the sums of the purple ones above. And the condition we have to check is that this number here has to be less than equal to the size of j. This case is 2, and it is. So, well, this didn't at least fail any of the checks yet. Okay, so it turns out that this cattle animal is indeed cuddly, and that's our next result. Okay, so oh, sorry, that's not quite our next result. We'll get there in a second. Okay, so building off of some work of Nagu on the shuffle algebra, we showed the following. So for any cuddly cattle animal, it indeed does belong to the shuffle algebra and not just the big shuffle algebra, right? I mentioned before, not all cattle animals belong to the shuffle algebra. And what's more, if you go to the elliptic Hall algebra, you get something that lies in this X11 space, okay? Okay, so now actually, let me explain. Okay, so we need an additional definition. Once you know that psi of h lies in the symmetric functions in this alphabet X11, well, then it's equal to some f of X11, right? Some ordinary symmetric function in this alphabet 11. Okay, and so we just need a name for that f. We call that the cub of the cattle animal h. Again, okay, so that's what this definition is up here. There's some plethistic adjustment we have to make, some sense of artifact of our conventions for how we deal with the elliptic Hall algebra. Okay, and so now our main theorem is the following: that this LLT cattle animal we constructed before, its associated cub is essentially the LLT polynomial. Okay, these are just two different ways of writing that. All right, and then out of this, we can deduce the corollary that I told you before for nabla. Okay, so in fact, we actually do this. We can do this more generally. All the things I'm telling you about generalized to mn here instead of 1,1, but I'm just simplifying for this talk. Okay, so let's see how nabla comes into play here. Just a brief sketch. Okay, so there's sort of several ingredients we need to put together. So Schiffman and Vassarot and Fagan and Somboliak constructed an action of the elliptic Hall algebra on the space of ordinary symmetric functions lambda. And the main thing we need to know right now is that under this action, the X01 alphabet acts essentially by multiplication by f, up to some plethistic adjustment. The other alphabets are sort of more complicated, involving Macdonald polynomials, but this one is basically just multiplication by f. And then considering this action, if you conjugate by the action of nabla, you can adjust sort of which alphabet you're acting by, okay? And in our specific situation, we're going to want to plug in 0, 1 here, m is 0, n is 1, and then act on 1. And that's going to basically tell us that nabla, so if we multiply by f followed by acting by nabla, is equal to just acting by f in the 1, 1 alphabet. Okay, and sort of notice, right, everything we did here with the cuddly cattle animals was in the 1, 1 alphabet. So that's sort of where nabla arises. And then we additionally have to connect that to this operation of taking the polynomial part. And there's a way to connect that to the action of the elliptic Hall algebra on the ring of symmetric functions.
Are you making any assumptions about m and n relatively prime or not when you're doing this?
Yes, sorry, yeah. These are only defined for m n relatively prime. Yeah.
But then you have this X11. Oh, I guess they're relatively prime. Yeah, but zero,
Yeah.
you count 0, 1 as relatively prime?
Yes, we count 0, 1, yes,
Okay.
but not 0, 2, right? And not 0, 0.
Okay.
Yeah. That's right. Okay. Right. So we have a general result here, right? We can get, if we have any cuddly kettle animal whose cub is F, we can get omega nabla of F by taking the polynomial part of that kettle animal. And we obtain as a special case the corollary I stated before for omega nabla on an LLT polynomial. Okay. So that's just a bit of context for sort of how this result comes out of sort of manipulations in the Schiffman algebra in its action on the ring of symmetric functions. I think I'm out of time, is that right? So maybe this is a good stopping point.
Yeah, I was gonna say we're getting close. So is this a good time to stop or?
Yeah, this is fun.
Okay. Well then let's thank the speaker. Let me make sure. Yep. And if there's any questions, feel free to unmute yourself and ask. Jonah, I had to mute you in order for there not to be a thing, so make sure to unmute yourself if you, and so you can answer
Want to
as well.
answer.
Feel free to type questions in chat if you would prefer that. If not, you can unmute and ask away. I like your naming convention, by the way. Cuddly cattle animals.
Can I ask?
Yeah.
Do you get? I mean, I assume you have the C alphas as a sub collection here because those are the LLTs in some form, right? For and I'm talking about the C alphas, the ones that come in as touch points of the Dick path picture.
Wait, aren't those not sure positive?
They're not sure positive, no.
Yeah, so they're not, then they're definitely not LLT polynomials.
Oh, okay.
But the Hall Littlewood polynomials are, which I guess are special cases, or I'm not sure, depending on the conventions, maybe they're special cases of like Hall Littlewoods or something.
Right. And then you're getting sure expansions. Are you actually getting by definition, these things are sure positive or?
No, so actually that's one of the applications that I was going to mention just in a second. So maybe I'll mention it now. So one of the applications is what some of my co-authors have already mentioned. We do prove the Lohr-Warrington conjecture for nabla to the m on any sure function, but you don't immediately get that from the cattle animal. So it doesn't give you, these polynomial parts are not manifestly sure positive. You have to work to get that.
Are they manifestly monomial positive?
I don't think so, no. In fact, they can be, they can often be actually not sure or monomial positive for certain cattle animals.
But then for these particular cases, they are sure positive.
Not quite. So yeah, that's an interesting question. So even for example, for the cattle animals for a single ribbon sure function, those ones are not sure positive. The ones for a single sure function though, a non-skew sure function are sure positive up to a sign. But that's like, it's a very interesting question to sort of understand that in general. We have in the paper, the paths under any line paper, or shuffle theorem for paths under any line that we posted in February. There's an interesting conjecture there for, it's not a special case of this LLT cattle animal construction, but it is a conjecture on certain cattle animals having sure positive polynomial part.
Are there other questions? So I guess technically Pear is asking, are there pictures of slides of dogs on the last few slides, or?
No, there's more math.
More math, okay.
How many more slides of math did you have? I'm curious.
Oh, a bunch. I mean, but I didn't expect to get to them. Sometimes I just put them in there.
Okay, so I guess Pear is waiting for Anna to give the talk for dogs.
Yeah, I will add a bunch of cartoons and animals.
Awesome. I'll have to watch your talk too. I love animals. Okay, are there any other questions, or if not, let's thank the speaker again. Thanks for the amazing talk, Jonah. That was amazing. That was nice.